All right, so let's go ahead and get started with today's lecture. We're pretty much continuing where we left off last time. So last time we talked about what a limit was. So real quick, can someone more or less, you don't have to give it to me formally, so either formally or informally, tell me what is a limit? What's the whole point or idea that we were talking about for a limit? What would you do if I said, give me the limit of as x approaches this number of this function, if I gave you a graph, for example? Yeah. So the whole point was for a limit, the end question is what y value are we approaching? Not what y value are we at, but what are we approaching? So we introduced the concept of the limit. We introduced a more or less formal definition. And now we're going to go ahead and talk about what if I don't have a graph for that function? What if I just say, give me the limit, so here on the board, of something over here where I have the limit of some algebraic expression. So starting us off, let's go ahead and talk about calculating limits using our limit laws. So there's going to be a long thing about limit laws. So the first thing I'm going to point out here for this class is that I'm not expecting y'all to regurgitate these word for word, because actually they're going to turn out to be very intuitive. So let's say that if I take the limit of f of x and then the limit of g of x, so I have two different limits of two different functions. And let's say that they do exist. So I was able to find them. So I want to take a pause here. Does anyone know what this symbol right here means? C and this little weird symbol in the middle, an R. Has anyone ever seen that before? You probably haven't, but what was that? Yeah, so if I look at this C, and it looks like it looks like a sort of a curved E. So this is actually sort of like an epsilon. So this means C is a real number. In other words, R stands for the real numbers. C is just a variable or a constant. And the symbol in the middle means that C is a real number. So if I let K be another constant, or in other words, K is a real number, that's all the symbol means. So instead of having me to write K is a real number, I can write this shorthand. And this is a common thing for a lot of math that you'll see in the future. And N is an integer. Then the following rules do apply. The first one is the sum/difference law. So if I want the limit of a sum or difference, so in other words, this limit of f plus or minus g, this is the same thing as taking the limit of each one individually and then adding or subtracting them together. So again, the limit of a sum is the sum of the limits, which is, again, just a fancy way of saying we can do each one individually instead of trying to do the whole thing. Gonna scoot this up a little bit. So that was our first limit law. The next one is called the constant multiple law. So if you have a limit of a constant times a function, that's the same thing as saying, that's equivalent to having that constant times the limit of the function. And just like before, right now we're kind of writing this very generally and broadly with all of these different letters and everything. You'll see that actually our calculation work is not going to be as intense as it may look initially. So we have the sum and difference law, the constant multiple law. And then I'll also mention the product law while we're at it, since it's on the screen. So the product law says that if I have the limit of a product, f times g, then that's the product of the limits. Again, just like how before, whenever I had sum and difference, it was telling me I can just do the limit of each one individually and add them, subtract them together. I can do the same thing for multiplication. I don't have to necessarily do the limit of the whole thing. I can take each individual portion and work on them. So I'll give y'all time to copy all of this down. And I really want to emphasize again, even though it looks like a lot of limit laws and everything, it's actually going to become a very quick, intuitive thing over time. Hopefully, a little bit more intuitive after we start doing some examples. And based off those first three, you can probably guess what's going to happen for the quotient law. It's pretty much going to be the same idea. I'm allowed to sort of split this operation into individual limits. So the reason why I'm introducing these limit laws is the idea that if I have something that's very complicated, a very big function, by using these limit laws, I can break them down into these sort of smaller, more manageable pieces. And if you're still copying, if you're done copying, you can probably go ahead and copy down this quotient law on the bottom as well. Hopefully once Blackboard is up and ready, then I'll be able to post these onto Blackboard so that you don't have to worry about getting every single, missing any details. So as I said, if you haven't copied down the quotient law yet, it follows the exact same pattern. The limit of a quotient is the quotient of each individual limit. And this rule applies so long as the limit of my denominator is not 0. And that can be explained very quickly as why we require that. Why do I not want the limit of my denominator to be 0? Yeah, so if I have that the limit down here, this whole bottom denominator is 0, then I'm getting some number divided by 0, which we know that we don't want to ever be dividing by 0. All right, so these are the first group of my limit laws. Sum difference, constant multiple, product law, quotient law. I think I still see a couple of y'all copying stuff down. I'll wait until y'all are done with that before I move on. And some good news for y'all, if you're saying that there's so much to copy, we're rarely going to be actually writing this out step by step whenever we actually go through the examples. It's just saying we have all this foundational theory stuff that we have to cover. I might write it on the board for just the sake of notes, but whenever we start actually doing like exams and stuff, it's not going to be very common that I'm going to be making you writing limit over and over and over again. All right, so let's go ahead and scoot up. There's some other limit laws that I want to cover. Next is the power law and the root law. So if I have the limit of a function to a power, that is the same thing as taking the limit of the function, whatever that might be, and then taking it to that power. So for example, if I was taking the limit of f squared, that would be the same thing as the limit of f, parentheses, all squared. In other words, I'm able to translate that square or the power to the outside of my limit. And lastly, we have this thing that we call the root law. If I have the nth root of a function, and I'm trying to take its limit, that's the same thing as taking the nth root of the limit. So just like before, it looks like the limit has a lot of these very nice translations through my operations. I'm able to almost switch out between my multiplication of the limit of a product to the product of limits. And actually, even though I've listed them as separate laws, 5 and 6, they're pretty much actually the exact same law. Why is that true that 5 and 6, the power law and the root law, are actually pretty much the same thing? Yeah, so if I look at this right here, if I take an nth root, like a square root, for example, a square root can always be written as a power. So since an nth root can always be a power, that's exactly the power law. The only reason, the main reason I put this as a separate thing is that we know that some weird things start happening whenever I introduce a square root. Like if I take a square root of a negative number, there's some complications with that. So these are the 6 limit laws that we'll actually pretty much be using for the first unit over and over again. All right, so now that we know these limit laws, let's go ahead and do our first example for today. I'll leave this right here in case anyone was copying that last one. So example 1, I'm going to be giving you a couple of limits. Let's say the limit as x goes to 2 of f of x is 4. The limit of g of x is 5. And the limit of h is 8. So I gave you 3 separate limits. And I want you to evaluate these following limits that I've listed here. So I have no idea what the function actually is, and I actually don't really care. All I know is that the limits as x goes to 2 of each of these functions are 4, 5, and 8 respectively. So I'll give y'all some time to copy this down. For part A, we're going to be looking at the limit as x goes to 2 of, to be very clear, in brackets, g of x cubed plus h of x. All right, so looking at part A, like I said, we have the limit as x goes to 2 of g of x cubed plus h of x. So looking at this, which limit laws do you think I will be applying for part A from that list of 6? Yeah, the sum and difference for sure, because there's an addition in there. What other limit law am I probably going to be using? So I got 6 of them. We're going to be using addition for sure, the sum. Yeah, so I think I heard someone say the power law because, well, there's a power right here, a power of 3. So we're going to be using those 2 laws. So what I'm going to be doing here is I'm going to be writing it step by step. Of course, I'm not going to be expecting y'all to necessarily put the step by step on the actual exams later on. So the first thing I can probably go ahead and do is I have a sum. I know if I take the limit of a sum, I can split this apart into its individual pieces. In other words, I can write this as the limit as x goes to 2 of let's write it this way. G of x cubed plus the limit as x goes to 2 of h of x. So this is just me applying my sum law. And really, I could have taken this one step further. What's one thing I can do to take it a step further? I can take out, well, what do you mean by taking out the limits?
Just don't write limit x.
Well, we still sort of need to write it because we're not just working with g of x, we're working with the limit of g of x. So we applied the sum law already. We also said that we were going to use the power law. So what can I do with the power? Bless you. Yeah, so using the power law, for the sake of space here, go ahead and erase this. I can actually take this a step further and write this as the limit, the limit all cubed. Remember, that's our power law. I can take the cube outside of my limit. Before it was inside my limit, now it's outside of my limit. All right, so I claim that we've pretty much done most of the hard work already. I claim that we can go ahead and start doing some quick substitution here. Well, right here, I have the limit as x goes to 2 of g of x. What is this equal to? 5, right? Because I gave it to you right in the instructions. The limit of g of x is 5. So really, I can write this as 5 cubed. What's the limit of h of x again? 8. So we have plus 8. Yeah, so let's see, 5 cubed, 5 times 5 times 5. So I get 5 times 5 is 25. Times 5 again, we get 125. 125 plus 8. Yeah, I get 133. And that looks like our final answer. So again, all I did was split this up into individual limits and then use my given information. So any questions about what I wrote for part A? All right, so take a moment and see if y'all can do part B on y'all's own. Here at the limit, x goes to 2 of, it might be a little bit hard to see, f of x minus g of x all over h of x. So the first thing you might be thinking about is what limit laws can I apply? I'm going to say that there's 2 limit laws that you could work with here. Not that you could work with, but you will work with. So once you get an answer, you can go ahead and just yell it out or tell it to me. What are y'all getting for part B? Yeah, I think I would agree with that. -1 over 8. Let's go ahead and talk about how we would get that. So I know that here I have a difference because there's subtraction, and I've got a quotient. So with if I apply those 2 laws, the difference law and the quotient law, I know that I'm just taking the limit of each one individually and then plugging them in. So what's the limit of f of x? We have 4, right? What's the limit of g? Yeah, we have 4 minus 5. all over, what's the limit of h? 8. 4 minus 5, we get -1 all over 8. And then we're done. So again, we're just applying these limit laws as we need. And again, notice here that I have no idea what f, g, and h actually are. I have no other information about that. All I know is that what their limit as x goes to 2 is. So yeah, that's going to be a good question. What happens for part C? I'm going to hold off because I'm going to need a little bit of space to explain what's going on there. Not a ton of space. It's going to be a lot more obvious than what you may be thinking. All right, so any questions about parts A and B before I move on to part C?
So we're just using the limits to help break down the problems and work it out from there.
Yeah, that's exactly what we're doing. Using our limit laws, we can take something that looks really nasty like this and then just break it down into its individual pieces one by one. All right, so let's go ahead and move on to part C. So for part C, we actually don't need the instructions for that one. I just have the limit as x goes to 2 of 19. So what's happening here? Well, first off, I don't see any sum, difference, multiplication, division. I don't really see any of that. But remember, I'm taking the limit of a function. In this case, my function is a plain 19. So this is a little bit of scratch work. You don't necessarily have to write this. So I'm taking the limit of the function. Let's call it f of x is 19. Or you can say y is equal to 19. Does anyone remember what does that graph look like? It's a flat line because it's a constant. In particular, again, if you want to draw it, here, my very quick sketch of it. Here's my x-axis, my y-axis. It's quite literally a flat line at 19. So if I take the limit as x goes to 2, 1, 2, what y value are we always approaching? 19, right? Because we can do the same thing as yesterday. I look at x equal to 2. As I come in from the left, I'm going to 19. As I come in from the right, I'm also still at 19. So what's the limit of 19? It's 19. So this gives us a very big limit law that I didn't include before. The limit of a constant is that same number. So if it was the limit of -42, then that would be still -42. Here's another question I want to ask about part C. Do y'all think anything would change if I took the limit as x goes to 44 of 19? In other words, if I change this number. No, it's not going to change anything because my function is flat the entire way. It's not change. My y value is not changing the whole time. So really, I could have changed this x going to whatever to any other value. It still would have been 19 here for part C. All right, so we have that example 1 done, part C. Any questions about what I just talked about for how we took the limit of, well, 19? So this is probably the problem that you would want me to put on a test because you're just like, all right, I just copy this on a number. And sometimes I put it on there just to see if people paid attention. Sometimes I don't. We'll see. Like I said, I don't really make the test until probably like 2 days before, maybe a week before if I'm really ahead of time. All right, so we've done that example. Now let's go ahead and put something a little bit more, where let's put a little bit more effort into it. Let's go ahead and look at example 2 now. Evaluate the following limit for some real number C. I don't know what C is, I just know it's a number. So for this example 2, we're looking at part A. And now I have the limit as x goes to some number C. I don't really care what C is. I'm just using it as a broad sense. Of the function x cubed plus 4x squared minus 3. I'll give you all a second to copy this down. All right, so for this example 2, part A, I'm going to give y'all an option. Y'all want the in-depth explanation, or y'all want me to tell me how to do this problem if I gave it to you on a test?
So we're just trying to solve it as one of the other, because it looks too familiar. It's x squared plus x cubed plus x squared minus number. Isn't that?
What was that? So in this one, what's going to happen is that I don't need a factor at all. I don't need a factor. In fact, I'm going to say that really I don't really need any calculations here. So let's go ahead and I'm going to take a side note here. What if I wanted this? The limit as x goes to, I don't know, 3 of just a plain x. Let's think about the function y is equal to x. What does that look like? Y is equal to x. If I were to graph this, or if you put this into your calculator and graph it. Anyone remember what that looks like? It kind of just looks like a diagonal line. Imagine that this is centered. It looks like that, right? Because whenever you plug in 1 in for x, you get y is 1. When you plug in 2, y is 2, so on and so on. It's kind of like a perfect 45-degree angle. So if I wanted the limit as x goes to 3, here is 3, and here is 3. What do you think that this limit is going to be equal to? 3, right? What if this was the limit as x goes to -4? It'd be -4 because it's this function where I'm just going directly diagonal across. So I want you to keep what I just mentioned there in mind. So now looking at this, I'm allowed to apply my limit laws. We're going to do this in a slightly longer way, just so that we can explain part A. I see a sum, addition. I see a difference, subtraction. And I see a power. And I see coefficients. So using my limit laws, one way I can write this right here is that this is equal to, there's going to be a lot of limits just for notes, x cubed. That's the first one, just x cubed, plus 4 times the limit as x goes to c of x squared. Again, there is a coefficient of 4. The square, I can take it outside. And then the same thing here, minus the limit of 3. I'm going to have to erase this side here for space. The limit as x goes to c of 3. So this is me breaking it down using those limit laws we talked about earlier. So it looks like all I have to do now is figure out what are these individual limits. What's the limit as x goes to c of x? So y'all told me before, if it was x going to 2, the answer would be 2, right? So if it's x going to c, it's c, because c is just any number. So this whole thing is c cubed plus 4 times c squared minus, what's that last limit?
Oh, C, 3C.
3c.
C
So,
times
so remember, what is the limit of a constant? It's that same constant, right? In this case, it's 3. Well, that's my answer. What are you noticing about the original problem and what I had here as my final answer?
everything is just C.
Yeah, it looks like I just plugged in C, right? Anywhere there was an X, I put in a C. That's not going to be a coincidence.
That's a- that's gonna be B.
Yep, you're probably seeing what's going to happen for part B. So looking at part B, I'm going to claim that you can do this without having to do all this extra work. Someone very quickly tell me what is part B, the limit of x goes to c of this very nasty looking quotient going to be?
Really want to say.
So c to the 4th. Kind of looking like I'm just plugging in c again. Because I can do that same process like before. I could, if I want, I can split this up saying it's the limit of x to the 4th plus the limit of x squared minus the limit of 1 all over this. But I know in the end, it's going to end up looking like I just plugged in c. So using what y'all know from parts A and B, I claim that y'all can do part C. This one's a limit as x goes to -2 of the square root of 4x squared minus 3. Using the exact same concept from what I had in the earlier two.
Minus 3.
Am I plugging in C?
Oh, well, C is named 2 these times.
Yeah, this time we're going to -2 instead of C. Yes. So I'll give y'all another second for anyone that hasn't finished writing it down or completing it yet. This time I'm taking the limit as x goes to -2. Because remember, C was just a placeholder for any number. But now I'm just saying, let's define what we want C to be. So just like how in parts A and B, it looks like I just plugged in C. I'm going to guess, based off a pattern, for part C, I'm just going to try to plug in -2. So if I just plug in -2, I get the square root of 4 times -2 squared minus 3, all that underneath a square root. And just so that you are familiar a little bit with my handwriting, whenever I do a square root, I usually like to put a little bit of a tail on it to say it goes all the way to that spot. All right, so we can do this calculation very quickly. -2 squared, I get 4. 4 times 4, I get 16. 16 minus 3, I get the square root of 13. We're done. So what I want y'all to take away from this example is that whenever I have a limit, if I can plug in the number and get something that's very clean and nice, then that's all we're doing. Because we know that any of these limits can be broken down individually into this basic limit here. No, you don't have to write all of that stuff. Maybe for this one, you would have to write this to show me, yeah, I plugged it in. but you don't have to write the limit of this plus the limit of that plus that. If you want to, you can. Again, I want to remind y'all, whenever we get to testing time in a few weeks, whenever that might be, I'm not necessarily looking, do you have the correct answer? I'm looking for, did you understand what we're supposed to be doing? Yeah, I would like it if y'all get the correct calculation, but I care more about, did you know the calculus behind it? I'm not going to be looking super hard if you know every single algebra thing out there. All right, so we're done with part C. Let's go ahead and move from here. But before that, any questions about this example before I move on? The long story short is if you can plug it in, then go ahead and plug it in. Yeah, let's see what's going on for example 3, or is that their example 3? Oh, a theorem. 2 theorems. Exciting. So theorem 2. Suppose I have a polynomial and a constant. Then this theorem is just reiterating what we just had earlier. So if you can plug in your constant and get a clean number, then there's no problem. Does anyone here remember what a polynomial is exactly? So you're thinking on a polygon. So a polynomial is exactly what we've been working with. If I have x squared, 3x squared plus x minus 2, stuff that looks like that. And theorem 3 is actually the exact same thing, saying if you can plug in your letter, your constant, and get a nice answer, then we're fine. So I've actually been using a little bit of informal terms. I said plug it in and we get a nice answer. But what do I exactly mean by quote unquote nice? What's something where if I plug it in, I might not get a nice answer? If I don't get a real number, or if I divide by 0, right? Those are things that are not so nice for us.
It's something we can easily work out much more.
So those stuff, whenever we have an imaginary number, like square root of a negative number, those get a little bit kind of everywhere. But whenever we're dividing by 0, there is something that we can do that we'll learn about later. In other words, we've got methods to deal with them. Some methods we'll talk about, some of them maybe not so much. In fact, we're not really ever going to talk about imaginary numbers in this class, because actually for calculus, if I want to give it a more formal name, it would be the calculus of real numbers. There's actually a whole nother field where we talk about calculus with imaginary numbers.
What calculus is that?
You probably it's complex analysis. Very big, very lots of nuances in that field. All right, so y'all looked at theorem 1 and 2. This was, again, just me formally saying, if you can plug it in, then plug it in. And so once again, just to reiterate what we know about those theorems, we can very quickly do parts A and B. So for example 3, I have the instructions, evaluate the following limit. So for part A, I have the limit as x goes to -6 of -8x plus 9. And then for part B, I have the limit as x goes to 4 of 8x minus 17. So as I said, you can probably guess what I'm about to do there. What do I need to do for part A? How do I figure out and evaluate this limit? Yeah, we're going to plug in -6 and make sure that we get a quote unquote nice value. So if I plug in -6, I get -8 times -6 plus 9. And then we're going to clean this up. What's -8 times -6? Yeah, so -6 times 8, I believe we should get 48. So we get 48 plus 9. And then what's 48 plus 9? Yeah, we get 57. And 57 is a nice number. We don't have a square root of a negative number. We're not dividing by 0. Even a fraction is a nice result. I'm not breaking any of my classic rules about numbers. And we're done with part A. So really at this point for part A, if I gave you something like this, I'm saying, do you know that you're supposed to plug it in? And then the second part is, can you multiply and add correctly here? So we have part A. Let's see if part B will be any different for us. Move this up here. All right, so part B, similar, same instructions. This time I've got the limit as x goes to 4 of x squared plus 3x plus 2 all over 8x minus 17. What am I going to do? We're going to try to plug in 4. And we're going to see, do I get a more or less nice answer? So plugging in 4, I get 4 squared plus 3 times 4 plus 2 all over 8 times 4 minus 17. All right, let's see how good y'all's quick math, mental math is. 2? Are we getting in agreement of 2? Or are we believing it right off the bat without checking? I don't know what it is. I don't know what this calculation is right away immediately. Let's check it real quick. 4 times 4, 16. 16 plus 3 times 4, 12. So 16 plus 12, I get 28. 28 plus 2, I get 30 on the top. On the bottom, 8 times 4, 32 minus 17, 15. So I agree. 30 over 15 definitely gives us 2. Yeah, unfortunately, this board has a lot of delay, but I'll get used to it eventually. All right, so part B, we plugged in 4 and we got a nice answer. Nice referring to I didn't divide by 0. I didn't get an imaginary answer. So 4, we're not going to exactly have the same nice thing. So example 4, we have evaluate the limit as x goes to 5 of x squared minus 25 over x minus 5. So initially, I would say, let's go ahead and plug in 5. But what's the problem?
Get 0 over 0.
Yeah, we get the biggest thing, 0 on the bottom. And usually we don't want to divide by 0. Because whenever we divide by 0, all of math starts breaking apart and it starts allowing weird things to happen. So is there any way I can get around this though for example 4? Okay, let's see. All I want to do is move you upwards. Will you let me do it? Yes. All right, so looking at this, we have x squared minus 25 all over x minus 5. Clearly, I can't plug in 5 because I would get 5 minus 5 on the bottom. But looking at this expression, x squared minus 25 over x minus 5, is there anything I could maybe do with that? Yeah, so looking at this, x squared minus 25, that is something that I can, not that it doesn't exist. We don't know that necessarily yet, but we can factor it. Because x squared minus 25, how can I factor that? So in other words, what I'm saying here is that I'm allowed to write this. X squared minus 25, that's the same thing as x plus 5, x minus 5. Why is that really good for us? So if I look on the top and I look on the bottom, I have an x minus 5 on the numerator and the denominator. In other words, you're giving me the limit as x goes to 5 of x plus 5. Why was that really good for me that I got rid of x minus 5?
So that way it turned out to be nice.
Yeah, because I know before that x minus 5 on the bottom, that was giving me a 0 on the bottom. So by factoring, I get rid of that problem I was having, leaving me with this new limit, x going to 5 of x plus 5. What can I do from here? Well, I got rid of my problem. Let's try plugging in 5 again. What happens whenever I plug 5 into here? And I get 5 plus 5, which I believe we all know to be 10. And then we're done with example 4. We finished this limit. So in other words, if it's possible to factor and cancel out our problem, then that's what we'll have to do. But otherwise, I always recommend try to see if you can plug it in first. If you can plug it in right away and get a nice answer, then we're done. If I can't, maybe I can factor and go from there and cancel out the problem. Any questions about what I mentioned here for example 4? So let me just look real quick what's left down here. I have another page. I don't think we'll be covering it today. We'll save these for tomorrow, example 5 and 6. Yeah, we'll save those for tomorrow. So I'll end it today at example 4. Like I said, tomorrow we'll do example 5 and 6. And we'll probably start the next section tomorrow also, because otherwise we'll probably only be here for 20 minutes otherwise. All right, so besides that, I'll see y'all tomorrow.